is my first lecture of partial differential equation PDE. Chapter 1 is first order partial differential equation and lecture 1, which I will be doing now. So first order PDE partial differential equation. Okay. Now first topic is about the curves and the surfaces. Okay. Now this session briefly describes two geometrical objects, curves and surfaces. Now they play a very important role in the study of PDE, these curves and surfaces. Okay. Now let us see the definition of the curve in space. A curve may be specified by means of parametric equations. Suppose f1, f2 and f3. Suppose if these three f1, f2, f3 are continuous function of a continuous variable t which varies in an interval I is a subset of R, then the three equations, now these three equations are very important. Okay. X is equal to f1 of t, y is equal to f2 of t, z is equal to f3 of t. Now this I will be using in one of the example later on. Okay. So this is very important, this curve equation of the curve. Okay. So now this represents the parametric equation of the curve in the three-dimensional space. A standard parameter is the length of the curve. In such cases, at times the symbol s is used instead of t. I hope you all can see the screen properly. So you all can take down this definition of the what is curve in space, and this is very important. This particular thing is very important. This three, which I will be using in the example as I told. Next is the note. Now this note is very important. Let us see the note, which is very important. The condition that the parameter t is the length of the curve is f1 dash square plus f2 dash square. Now this is f1 prime square plus f2 prime square plus f3 prime square is equal to 1. Where prime denotes differentiation. Okay, now these are the primes. This dash or everywhere I put dash, no, that is the prime, that is denoting the differentiation. You are differentiating what you are differentiating? We are differentiating this f1 of t, f2 of t and f3 of t. Okay. So this note is very important. Even again I am telling you all that this is being used, meaning I will be using this in one of the example. Let us take one example now. The simplest example of the curve in space is a straight line with a direction cosine lmn passing to a point x0, y0 and z0 with parametric equation. X is equal to x0 plus ls, y is equal to y0 plus ms, z is equal to z0 plus ns, where s belongs to R. Okay, so this example you can take down. Then there is one more example which I have to explain you on. A right circular helix is a space curve lying on a circular cylinder, and is given by the following parametric equations. That is x is equal to a cos wt plus comma y is equal to a sin wt, comma z is equal to kt, where t belongs to R, where a, w and k are constants. So here this is the example. Now I have to give you all the solving part. So what is my x over here? Okay, so let me explain you all this. So now we have to see the equation of the curve. Okay. So we have to see the parametric equation of the curve. This. Now I will be using this. Okay. Now this is nothing but x is equal to f1 of t. Here it is for this one. Y is equal to f2 of t and here for this one it is z is equal to f2 of t. So here what we are going to do is, this node is very important. As I said, the condition that a parametric t is the length of the curve. Now what we have to do for the f1, f2, f3, now these are the primes, so we have to differentiate it, right? So what we have to do is, we have to differentiate this x, y and z. Okay, so that's what I have to do here. Now what is my x? X is nothing but a cos wt, then y is equal to a sin wt and z is equal to kt. Now first I will differentiate this. Dx by dt is equal to, now I am differentiating this one. Okay, wait. Okay, so what I have done here, x is equal to a cos wt, I have differentiate. Okay, dx by dt is equal to what is the differentiation of this? Minus a w sine of wt. Okay, and then dy by dt I will differentiate this and I will get aw cos of wt. Then I will differentiate this, I will get dz by dt is equal to k. Okay, once you differentiate, what you all have to do is, let me do it here, f1 dash square plus f2 dash square, this is primes, okay, plus which are denoting as differentiation, is equal to 0. So I have to substitute, is equal to 1, no? In that note, I have already given this to you all, that it is equal to 1. So now this is dx by dt is equal to this. Differentiation of this, then differentiation of this is, I have written it over here, and differentiation of this I have written it over here. Now you will have to substitute all these three values in this. Okay, and what is this? From the note I have taken, right? Which note it is? From this note. The condition that a parameter t is the length of the curve is f1 prime square plus f2 prime square plus f3 prime square is equal to 1. Okay, so from here I have taken that. Then I have to substitute in this particular thing. So what I have done over here is, I have substituted the values in this, the value of whatever f I have found out over here, I have substituted that is a square. So that minus sign will go. Okay, when I will square it, so it will go. So a square w square sin square wt plus a square w square cos square wt plus k square is equal to 1. Okay, so this is your f1. Then this is your f1 prime square, f2 prime square and f3 prime square is equal to 1. Okay. Now this a square w square is common. So take the common outside. Okay. So a square w square is common. So what remains? Sin square wt plus cos square wt plus k square, which is not equal to 1. Okay, now this implies that a square w square plus k square is not equal to 1. So with this I am done with today's lecture. In the next lecture I will be doing the topic on surfaces. Okay, and thanks for watching.